an IVP means it's a differential equation, and along with that we have this initial condition. So that means whatever solution we are trying to find, that has to satisfy that condition also. So there will be only one solution. So let's see the solution. We are going to be very sketchy in writing this solution, not in the sense that we are going to leave out details. We would write all the mathematical details, but we won't write sentences. For example, we don't even say what m and n are here. You already know what they are. This is m and this is n. So what we did here is we did write what m and n are, but in simplified form. So what do you do for this simplification? Obviously you do the divisions. So if you divide 1 by this denominator, then this becomes x to the power minus 2 over 3 times y to the power minus 1 over 3. And then when you do that same thing to this second term, 8 of course stays 8, and then x divided by x to the power 2 over 3 is x to the power 1 minus 2 over 3, and 1 minus 2 over 3 is 1 over 3, 1 divided by 3. On the other hand, 2 over 3 minus 1 over 3 is the exponent of y, which is again 1 over 3. So that's how. This one is more manageable than that one. I mean, as far as differentiating it is concerned. Similarly, we also simplify the n. So what is, we do the same thing here. This one of course stays unchanged, 2 times x to the power 4 over 3, and then y to the power 2 over 3 minus 4 over 3. So minus 2 over 3, minus 2 divided by 3, minus, this one is very easy. This one is a power of x, this one is a power of y. So simply x to the power 1 over 3, y to the power minus 4 over 3. And then we do the differentiation, partial differentiation. So we first differentiate m with respect to y. So that means all the powers of x will be considered constant. So this term will give you what? Minus 1 over 3 times y to the power minus 1 over 3 minus 1, which is minus 4 over 3, and this thing stays as it is. And then the second term gives you what? We are differentiating with respect to y. So this will be considered constant, and this time again 1 over 3 comes down. There minus 1 over 3 came down and gets multiplied with 8, and 1 over 3 minus 1 is minus 2 over 3. So that way you get this one, and x to the power 1 over 3 stays here. But will you really get the same thing if you differentiate n partially with respect to x? Let us see that also. So if you differentiate this partially with respect to x, what are you going to get? When this 4 over 3 comes down and gets multiplied with 2, you get 8 divided by 3. So that means you guess that this is the term that you should get. Will you really get it? You see, already you are having y to the power minus 2 over 3, and your differentiation is with respect to x, so y should not change. So it will stay like this. And when you subtract 1 from the exponent of x, which is 4 divided by 3, you get 1 divided by 3. So yes, you are actually getting this term by differentiating this partially with respect to x. And then what does this term give you? Again, the differentiation with respect to is with respect to x. So this 1 over 3 will come down, and already there is a minus, so minus 1 over 3 times x to the power 1 over 3 minus 1. So that is minus 2 over 3, and this one stays unchanged. Yes, the partial derivatives match exactly, and that too, this is happening for all x and y. Well, keeping in mind that x and y are both non-zero because of these things. Okay, they are not both non-zero. So what does that mean geometrically? For x and y to both be non-zero, it means that the point x comma y on the plane lies neither on the x-axis nor on the y-axis, and the origin is one point among all these points. So it's not simply that our point x comma y is not the origin, but also not on the axis. Elsewhere on the plane we have this equality. So obviously there are infinitely many rectangular regions in which our equation is exact. Okay. So then what shall we do? Same procedure. The equation is exact means there exists an f for which so and so things will happen. So let's do the rest now. So there exists an f for which these so and so things happen, that the partial derivative of f with respect to x is m and the partial derivative of f with respect to y is n. Okay. And then what do? We integrate both sides of the first equation with respect to x, and then an arbitrary function of y will appear. So those things. So let's do that part next. I have kept this condition here. I haven't erased it because we may forget it. Okay. Not that we will forget the values 1 and 8, but we may actually forget about it altogether. That is why I have kept it. So by actually doing that integration, this is what we get. On the left hand side, of course, we will have our f. Now let us carefully integrate this expression with respect to x, considering y as constant. What are we going to get from this power of x? When we do integration, we add 1 to the exponent, so we get a number, and then we divide by that number also. What do you get if you add 1 to minus 2 over 3? You get 1 divided by 3. So that means now you will have x to the power 1 divided by 3, but divided by 1 divided by 3. So that means you have to multiply by 3, and y to the power minus 1 over 3 is constant. What are you going to get from this second term? If you add 1 to 1 over 3, you are going to get 4 over 3. And when you divide by 4 over 3, and that 4 and 8, they can get cancelled, 4 gets cancelled, 2 remains. So 2 remains in the numerator, and there is a 3 in the denominator of the denominator. So when it goes up and gets multiplied with the numerator, you get 6. And that here, of course, you already had 4 over 3 when you added 1 to this 1 over 3. So that way you get this term, and this one, of course, stays unchanged, plus phi of y, where phi is an arbitrary function of y only. And then what is the next step? Next step, of course, is to differentiate both sides of this equation partially with respect to y, so that we can use this second condition. So let's do that next. Instead of cramming everything on that side, I have done the calculation on this side. So because we are anyway going to use this, so I start with this expression, that is equal to del f del y. And now we are going to also get del f del y by differentiating this expression, this right hand side of this equation, partially with respect to y. What shall we get if we do that? Minus 1 over 3 comes down. Remember, you are differentiating partially with respect to y, so x is considered constant. When that gets multiplied with 3, you get minus 1. So that's how you have minus here. And x to the power 1 over 3 will stay as it is, unchanged. After you subtract 1 from this, because you are differentiating from this exponent, what do you get? Minus 1 over 3 minus 1 is minus 4 over 3. Okay. And then what does this one give you? This 1 over 3 comes down, gets multiplied with 6 and gives you 2. The power of x stays unchanged, and when you subtract 1 from 1 over 3 this time, you get minus 2 over 3. And plus, again, do not forget that we also have this Here it's a function of y only, so partial derivative turns into ordinary derivative, phi prime of y. Now you see that very nicely, actually you are getting all these things back. Okay, whatever you have here, that is just there, and this one is just there, but plus you have this extra phi prime of y, so that is equal to 0, which means that phi of y is equal to constant. And as we always do with this type of situations, we do not write arbitrary constant here itself, we write it finally in the general solution. So we are going to conveniently take 0 here. Actually you can take any real number, but we are going to conveniently take 0. So after you do that, after you take this to be 0, you use that here. You go back to this equation and use that here. So that way this is your f with that special value of phi of y. So it is just this. And what is the general solution then? The general solution is f equals an arbitrary constant. This time we write an arbitrary constant. That means this expression is equal to that arbitrary constant. Now this is the general solution or a one parameter family of solutions, because you can change this constant and get different solutions. There are infinitely many solutions here, as many as there are real numbers. But this is not the end. You have this initial condition also. So now you have to find the value of c which will make that happen, for which when you take x equal to 1 and y equal to 8, you get identity. So let's now calculate c. So to calculate c, you straight away take the this value of x, that x is equal to 1 and y is equal to 8, and put them here, and then you see what your c is. Note that these things, these values 1 and 8 actually have been carefully chosen so that we do not get too much complexity, because roots are involved, cube roots. So 8 has been chosen because the cube root of 8 is 2. I said the cube root because I am talking about real cube root. So if you put everything here, then ultimately you get 27 divided by 2. Please go through that calculation in detail, and if you spot any mistake, let me know in the comments below. So this is your value of c, and when you get back to this equation and put this value of c, then that solution is the actual solution of the initial value problem. Did you notice one more thing? How ugly and haphazard it looks if we do not write it as a formal solution. Formal solution will be long because it has sentences, everything has its proper place. But it is clear, it is presentable. This one is ugly, however, this is how things appear in your mind. They never appear in an orderly manner. They will always appear like this, something here, something there, and then you try to make connections. So let me just end this video here itself.